Hi everyone, welcome to this seminar. For those of you who don't know me, my name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. And it's my absolute pleasure to welcome you all to this joint seminar with the University of Seoul. Our speaker today is Professor Sang, who will be talking about learning invariant representation. Professor Sang is an assistant professor at the University of Seoul. He's the director of the Machine Learning and AI Lab, and his research in machine learning focuses on multimodal learning, invariant representation learning to improve the generalization performance, and its application in diverse domains for machine learning deployment in the real world. He earned his PhD, master's, and undergrad from Carte, and in 2018, he was the visiting researcher at Neighbor Clova AI. With that introduction, I'll just pass the floor to Professor Sang. The floor is yours.
Okay, thank you. Then I will start the seminar. Good afternoon and good morning. My name is Kyungwoo from University of Seoul. First, I would like to thank the University of Seoul and University of Toronto for allowing me to give this talk. The title of my presentation is Learning Invariant Representation. And if you have any question, please type the question freely in any time during the seminar. This is today's content. First, I will present the spurious features and machine learning. Second, I will present the concept of the invariant representation learning. After that, I will introduce diverse methods for invariant representation learning. Firstly, I will present the interesting result of current machine learning model. The machine learning model learns the meaningful patterns from training dataset, and it works well. However, there are diverse datasets that we didn't observe yet. Besides, even at this moment, the dataset is constantly being created anew. The goal of machine learning is to enhance the performance of unseen dataset. However, the sample dataset might be biased and it cannot represent the full dataset. We can only observe some specific samples. Therefore, when we train the model on the sample training dataset only, then it may not perform well on the new dataset. This is a famous example that represents the problem of current machine learning models. The left image is taken from Philippines. Many machine learning models predict the given image as a beer or bottle. However, the ground truth label is spices. The right image is taken from Nepal. All machine learning models classify it as a food because the yellow part seems cheese. However, the ground truth label is soup. It is hard to know the exact reason for the machine learning problems. However, we can guess that one of the reasons is that the model only learns the given dataset pattern. Let's assume that we only collect a Western wedding dataset and we train our models. Then, model will classify the white dress or black suit as a wedding feature. Therefore, the model might be hard to classify the given another wedding image because the data is not trained. Because of this reason, it has been known that the machine learning model accuracy is proportional to the GDP. These are another examples. When we increase the resolution of the Obama image, the current ML restores it as white. In the past 2 or 3 years ago, Twitter selects the representative image automatically from the given diverse uploaded images. Twitter users found that the selected representative image is always white instead of Asian or black. At that time, Twitter advocated that each algorithm is fair, but it just prefers the bright color. To validate the hypothesis, Twitter users upload a white image with a dark background. However, the Twitter algorithm still selects the white image instead of Asian or black as a representative image. This is another example. Kyungwoo is my name. and Kyungwoo is my name. And when you translate the sentence such as Kyungwoo ate 100 apples, then it translates where? Kyungwoo ate 2,000 apples also, it translates where? However, if we are to translate the sentence, Kyungwoo ate 2022 apples. It denotes the year in Korean, not the number of apples or data set. All of these failure cases stem from the correlation, not the causality. Most training image has a correlation between the person and the race. Most training sentences has a correlation between 2022 and the year, not the number of apples. In short, the current machine learning runs the spurious correlation and it may degrade the performance in the real world. Then, how can you solve the problems? What we want is to construct a performant machine learning model across all groups or all environments. Group and environment are somewhat different, but I will use them interchangeably. Let's assume that we have two environments or two groups. The first environment is for a boat on the water dataset. The second environment is for a boat on the road dataset. We want that our machine learning model shows great performance in both environments. To achieve our goal, we need to run the invariant features and the shared feature across the environment. In this case, the background is spurious features that might degrade the model performance. In this case, the object, the boat, is a shared feature across the environment, and it is an invariant feature, and it is a causal feature that caused the label boat. It is also known as the parent of Y because it caused the label Y. I will use the invariant features, causal features, and TAY, parent of Y, interchangeably. From now on, I will cover invariant representation learning and its diverse methods. First of all, we will review the invariant features briefly. To get a competitive performance for all environments, including the most disadvantaged environment, constructing the invariant feature is important. We will denote the invariant features as PAY, the parent of Y. In short, invariant features can be interpreted as a causal feature that caused the label Y. Let's see the tabular dataset example. We bring the example from the adult dataset, the benchmark dataset for fairness. What we want is to determine whether a person makes over $50,000 or not. Besides, we will assume that the occupation and hours per week are the parent of Y, the invariant features that cause the label Y, and other features are spurious features. On the tabular dataset, we can just utilize PAY as an input features if we know the PAY exactly. Then the model can predict Y where based on the invariant features without any spurious correlation. The tabular, in short, for the tabular dataset cases, it is easy to get invariant features. Besides the tabular dataset, we will see the image and text dataset example. You will already be familiar with the car and boat example, right? The first example is to predict whether the image is about a car or a boat, the object, not the background. And the second example is to predict whether two sentences have an entailment relationship or contradiction relationship. The left figure denotes the training dataset. If we collect the dataset without any consideration, the background of most car photos is a road, right? Similarly, the background of most boat photos is a water. In this case, the machine might focus on the background instead of the object, because the background is distinct features and it is enough to minimize the training loss. In short, the machine might learn the non-invariant features or spurious features, the background. It will cause a problem when we encounter the new image on test time, the boat on the road. Then the machine might classify it as a car because the background is a road. I'm sorry. The problem is not limited to the image example. We bring the sentences from the MNLI dataset, one of the benchmark dataset for NLP. The task of MNLI is to predict whether two sentences have a contradiction relationship or entanglement relationship. Among the dataset, most contradicted sentences have a negation expression, such as never. Therefore, the machine is enough to learn the correlation between the negation and contradiction. However, it is not an invariant feature or causal feature, and it may cause a performance degrade. As you can see, when the model encounters that kind of sentences, the little girl is sad and the girl is not happy. We know that two sentences are not contradicted. They have entanglement relationship, right? However, the machine might classify it as a contradiction because of the negation expression. In short, what we want is invariant features. How can you make the machine focus on the invariant features instead of the spurious features? The simplest idea is that injecting the invariant features only into the machine. As you remember, it is relatively simple for a table dataset if we know the invariant features, the parent of y exactly. We just inject that invariant feature columns only into the machine. What about an image? Can we inject the invariant features only into the machine easily? Let's see the image case in detail. In the left case, the invariant feature is the object, not the background. However, it is not trivial to extract the invariant features only in the raw image. In the right case, the invariant feature is the digit, not the rotation angle and thickness. The digit is the invariant feature. Similarly, it is not trivial to extract the digit features only without rotation angle and thickness features. They cannot be separated easily. To recap, injecting the invariant features only into the machine is not trivial for image and text dataset. Therefore, we usually inject all images and text into the machine. When you train the image, we usually adopt the neural network-based feature extractor and classifying, right? We expect and we wish that the extracted features H include the invariant features, such as object only. However, in reality, the H might include undesirable features such as background. It may cause a problem when the machine encounters the image such as boat on the road dataset. Then the machine might be fair to classify it. When the extracted features include undesirable features, it might cause a problem, right? How can we encourage that the extracted features only focus on the invariant features, such as the object, not the background? What we want is that H includes the both features for boat on the water image or boat on the road image. To learn the invariant features, the most intuitive approach is data augmentation. Let's assume that we only have that kind of images, such as boat on the water and car on the road. When we train our machine on the trained dataset only, it will cause the problem as the previous, right? What if we can train more diverse datasets, such as boat on the road and car on the water? Our machine is able to know that the background does not indicate the label directly anymore, right? Therefore, our machine starts to focus on the object itself, the invariant features. In summary, the first strategy is to augment the dataset. and train our machine on both original dataset and augmented dataset for invariant representation learning. Let's think about the problem in detail. Can you generate the image such as car on the water and boat on the road easily from this trained dataset? It is not trivial to generate that kind of image based on the boat on the water and the car on the road image. In other words, data augmentation is not trivial, and it is not always possible. Then how can you achieve invariant feature learning in that case? Another approach is to regularize the extracted features H1 and H2. Let's assume that we have two environments, both on the water dataset and both on the road image. In short, we assume that we have bias label or environment label. In short, we know that environment 1 dataset and environment 2 dataset. This is the assumption. What we want is to make extracted features H include the invariant features, the shared features across the environment. In that case, the both, right? We regularize the extracted features H to focus on the both objects, the invariant features. We summarize the problem cases and their approaches. The first case assumes that we can augment the dataset to generate a diverse environmental dataset. The second case alleviates the data augmentation assumption. When the augmentation is not trivial, we can utilize regularization-based approach to learn the shared features across the environment, right? Lastly, the third case assumes that we cannot utilize the environment information as well as data augmentation. From now on, we will cover each problem cases and each detailed method. If we have any question, please type any question in any time, freely. Okay, I will start again. From now on, I will cover the learning method based on the data augmentation. Case 1 scenario. We will cover the first case that the data augmentation is possible. In this case, we bring the rotated MNIST dataset. Let's assume that we have non-rotated 0 and rotated A in the training dataset. The task is to predict the digit number, and the rotation angle does not cause the label, right? Therefore, we want that our machine to run the invariant features the digit only, not the rotation angle or thickness. Then we will rotate the given image. It's easy to augment the data set, rotated image, right? We will rotate the given image to run the digit information, not the rotation angle. For the given digit 0 image, we can generate diverse augmented data sets such as 15-degree rotated 0 and 90-degree rotated 0. After we generate the augmented data set, we let the machine run the original image and the augmented image. After that, we will introduce some constraints to extract invariant features. The first approach is to match the output of the machine. We restrict that the output of the original image and rotated images are the same. Because of the output restriction, the machine produces the same output whether the images are rotated or not. The second approach is to restrict the extracted representation, not the output. Representation invariance constraint encourages that the representation attend to the shared features, the digit in this case. For the generative model, such as the variational autoencoder, we can interpret the representation restriction as a posterior regularization. Another approach is to average the output of the machine. We utilize the average of the machine's output as our prediction. In that case, the machine produces the same output, whether the images are rotated or not. Until now, we have handled the case 1 situation where the data augmentation is possible and it's very easy. Let's imagine the more realistic settings. Even though we can augment the data set such as rotation, the optimal rotation angle might be unknown. Besides, the real dataset has much more complex features. For realistic images, the previous data augmentation is not trivial. For example, it is hard to change the background from water to road while preserving the photo image. This is a color amnest dataset, and the training dataset is strongly correlated with the color and vision, right? Therefore, the model considers that the red color denotes the zero, and it fails to classify the test image. The data augmentation for this case is also not trivial, because the optimal color or optimal data augmentation policy is not known. Therefore, we present a new learnable data augmentation method that utilizes the visual prompt. Let's assume that we have parameters that have the same size as the original image. When we add two images, we can generate diverse any images flexibly, depending on the parameters or visual prompt value, right? In this case, the visual prompt has the same size with the original image, and visual prompt parameters can be any value. Then we can, if we add two images, image and visual prompt, then we can generate any flexible images, right? So this is the ideal case. This is the illustrated image examples. Ideally, we can generate a background color augmented image and a background removed image if necessary. In short, visual prompt is a very effective method to augment the dataset flexibly. To convert the given image flexibly, each image should have its own visual prompt, right? Therefore, when we have n images with 224 by 224 size, then we need that kind of visual prompt parameters. Therefore, the number of learnable parameters for visual prompt is very large. Besides, it is hard to make the visual prompt for the test image. Therefore, we propose an autoencoder that generates the visual prompt with respect to the given image. We parameterize the visual prompt as a neural network output. Then we can generate diverse data-dependent visual prompts with fewer parameters. We adopt a pre-trained neural net as an encoder, and we only run the lightweight decoder to generate a visual prompt. In this case, we only utilize 9K learnable parameters to generate a visual prompt. It is noted that we can achieve invariant feature learning with data augmentation only. In short, we do not change the model structure. Therefore, our method is adaptable to diverse model APIs such as GPT or Click. From now on, I will present another method for the invariant representation learning, the case 2 scenario. From now on, we will see the case 2 when the suitable data augmentation is not trivial and is not possible. Given the boat on the water data set, augmenting it to the car on the water data set is difficult, or boat on the road data set is not difficult. We need different approach instead of the data augmentation. To get a high-level idea, let's assume that we have two environment data sets and we can train each environment independently. The first environment is boat on the water, and the second environment is boat on the road. There are 2x2 cases whether the first and second feature extractor runs the object or background, right? The first feature extractor can run boat or water, and the second feature extractor can run boat or land. There are 2x2 cases. The ideal case is that both feature extractors attend to the both object, not the background. This is the ideal case, right? Then both feature extractor run invariant features. In that case, the optimal classifier W1 and W2 are the same because they just need to classify the both object as the both. If if two H1 and H2, both of them runs both objects simultaneously. The natural question is, what if the optimal classifier for each environment are the same? When the optimal classifier should be the same across the environment, the feature extractor should attend to the both image, whether the images are the both on the water or the both on the road, right? In short, when the optimal classifiers are the same across diverse environments, then the machine starts to run the invariant features. Okay, there are one questions. Because of my issue, it is hard to check the Q&A right now. So I'm sorry, but I will reply the Q&A at the end of the session. Okay. Therefore, the IRM introduces the following constraint optimization problem. In short, the main idea of the IRM algorithm is that enforce that the optimal classifier across the diverse environment should be the same. Therefore, the IRM introduces the following constraint optimization problem. IRM constrains that the optimal classifier across the environment are the same. Besides, IRM minimizes all the environment traditional training loss also. The constraint problem requires complex multiple optimization loop. We can approximate the optimization as follows. The approximated IRM combines the traditional training loss and the gradient regularization loss. Minimizing the gradient of the loss with respect to the classifier indicates that the minimization of the classifier sensitivity across the environment. It induces the same optimal classifier across the environment. Another approach for invariant representation learning is to focus on the disadvantaged environment who are the worst group. Our usual training dataset might contain more environment 1 dataset, both on the water, than the environment 2 dataset, both on the road dataset. Therefore, the machine will attend to the environment 1 to reduce the average training loss, because the environment 1 dataset is much more than that of environment 2. As we see earlier, then the machine will focus on the background, not the both object, because the background is the most distinct features. How can you alleviate the problems? One of the solutions is to focus on the disadvantaged environment first. When we let the machine focus on the disadvantaged environment, it will focus on the invariant features, the both object. Let's assume that the machine focused on the road background, not the invariant feature. Then the machine will have a low training loss in environment 2, right? However, the machine will have a high training loss in environment 1 because there is no relationship between the road and the boat. It is noted that the number of data set of environment 1 is much more than the environment 2. Therefore, the machine tries to focus on the both object itself when we make the machine attend to the disadvantaged environment first. In short, training the disadvantaged environment mostly is helpful for invariant representation learning. We can formulate the idea as follows, and it is known as group DRO. Until now, for the case 2 scenario, we introduced two algorithms, IRM and group DRO. The major concept of IRM and group DRO is reasonable. IRM encourages that all environments share the same optimal classifier. Group DRO attend to the disadvantaged environment. However, they still have limitations. In the case of IRM adopts the approximation technique for the bi-level optimization, and invariance is not theoretically guaranteed yet. In the case of group DRO, it only handles the interpolation of the training environment, and it requires strong regularizations. Besides, both IRM and group DRO can only access the training environment, usually, right? It has been known that group DRO runs invariant features on classification tests when we can handle all environment. However, we cannot access to all environment data set in most cases, right? Therefore, the superiority of IRM and group DRO is not theoretically guaranteed when we handle the test environment that are sufficiently different from the training environment. There are recent papers that report the empirical limitations of IRM and group DRO also. The domain bed is a well-known test bed for the domain generalization that covers diverse datasets. For the domain-based dataset, IRM and group DRO show even worse performance than the vanilla ERM model. We checked the similar limitation empirically on the waterboard dataset. Waterboard dataset consists with two types of background and object. Waterboard on water, landboard on water background, and waterboard on land background, and landboard on land background. The disadvantaged environment is the anti-diagonal, waterboard on land and landboard on water. From our findings, group DRO improves the disadvantaged environment accuracy compared to the vanilla model ERM. However, the disadvantaged environment accuracy is still lower than the average accuracy. Besides, we find that the extracted features from group DRO still contain undesirable features background. When we classify the background based on the extracted features from group DRO, the worst case optimization is easily classified. In short, the extracted features from group DRO contains spurious features or not. We can check that the IRM has the same issue. To solve the problem, we propose a distinct representation of learning based on the conditional VAE and contrastive learning. Let's assume that we have two group images, a boat on the water and a boat on the land. What we want is to disentangle the invariant features and variant features. In short, the boat object and the background object. We encourage the model that the first latent vectors contain invariant features, while the second latent vectors contain the variant or spurious features. To encourage the model to run disentangled representation, we make the first latent vectors get closure across two environments. It is noted that the first latent vector is invariant or shared features across the environment, so it should be the closure. Therefore, we need to make it closure. To make a closure between two latent vectors, we utilize the KL divergence. To make bar between two latent vectors, the naive approaches are followed. First, minimize the negative KL divergence, or minimize the inverse KL divergence. Then, two latent vectors might become far. Right? Our strategy is to disentangle two latent features, invariant features, and spurious features. Then, invariant features or shared features are shared across all environment. So the first latent vector should be the same across all datasets. And the second latent vector is a spurious correlation, and it could be changed on the dataset, so it should be far. However, as you can see, the negative KL divergence is unbounded, and the inverse KL divergence might not be stable. Therefore, we propose variants that adopt exponential into the negative KL divergence and 1 plus to the inverse KL divergence. From our model, we improved the significant performance improvement. We analyzed our learned penultimate layer hidden features. The hidden features learned by our model contain label features or causal features instead of spurious correlation. Therefore, our model has high label accuracy, and our model shows very low accuracy on spurious correlation, spurious label prediction. In short, the extracted features from our model does not contain the spurious features, and it only contains the label features or causal features. We can check similar results from the TSNE visualization. Besides, we find the new limitation of the current group DRO and IRM and each diverse variance. The well-known variance is VREX. VREX group DRO and VREX tries to achieve the same training loss across all groups. In other words, the group DRO and VREX minimize the worst case training loss as much as other group. In short, the worst group and the best group have the same training loss on VREX to increase the generalization performance on worst group. When we apply VREX on a regression task, we find two limitations of VREX and group DRO. It is noted that this is the first study of a regression task based on the worst case optimization. By collaborating with Etri in South Korea, we tried to solve the pressure estimation task based on the biosignal. We find that the vanilla ERM model fails to estimate the pressure on the worst group, crisis. Actually, the crisis group has the smallest number of data sets, and we find that spurious correlation degrade the model performance on regression task also as much as classification task. Therefore, we decided to apply group DRO or VREX to solve the problem. When you apply VREX or group DRO, we find that the worst group loss, test loss, is still much higher than that of other groups. In short, VREX has the same training loss across all groups. However, the test loss does not satisfy the condition. Second, we find that the distance between the median and the group median is important. As you can see, the machine learning model shows great performance in the median group. However, the performance degrades for the extreme range of the group. Different from the classification task, regression is to estimate the ordinal value, and vanilla machine learning model is prone to predict the median value instead of the extreme value to minimize the loss. Therefore, the distance between the group median and the data median is also important from our findings. From two findings, we formulate a new objective, the ordered risk minimization. Based on the number of data sets and the distance between the group median and the data median, we select the worst group. Next, we minimize the training loss of the worst group more compared to the other group. In short, VREX only considers classification task and it forced the same training loss across all environments. Different from VREX, ORM, our model considers regression task and it shows great performance improvement. In short, the worst group or invariant feature learning were studied a lot in classification task, but from our findings, we conjecture that there are very rare research work that explores the regression task and the invariant feature learning. This is the last chapter of today's presentation. The last case of today's presentation is that we do not have environment label as well as the optimal data augmentation policy. Introduced the model in the presentation, including IRM, group DRO, and our diverse variants, require the environment labels, environment 1 or environment 2, right? We need an environmental label. However, the environmental label or bias labels are not always accessible. The label annotation cost is expensive and it could have a privacy issue. how can you learn the invariant features when we encounter the case study? There are no separate label. Which one is environment 1 or which one is environment 2? How can you solve the problem? The direct approach is to infer the environment label, because if we can infer the environment label from this data set, such as this one, then we can adopt group theory, IRM, or other diverse invariant representation learning methods. So the problem is, how can we infer the environment label? To infer the environment label, we will utilize the principle of IRM and group theory again. The principle of IRM is all environments should have the same optimal classifier for the invariant feature learning. IRM principles reduce the difference between the environments, right? It means that violating the principle of IRM incurs the difference between the environment. Therefore, we can infer the environment of each dataset instance. Similarly, we can infer the environment based on the group theory principle. Group theory principle is the most disadvantaged environment has the highest training loss curve. It denotes that each environment has a different training loss curve. Therefore, we can infer the environment label based on the training loss curve. In this presentation, we cover the major idea for the invariant representation learning. For the invariant representation learning, we introduced the diverse approach, the data augmentation, and the regularization-based approach. However, both approaches require an environment label or some specific assumption. Besides, we observed that the previous approach still contains undesirable hidden features, and invariant features learning is still a challenging problem. Also, there are very rare works that find the relationship between the regression task and the invariant representation learning. In other words, invariant representation learning is still open problem in my opinion. Because of the time limit, we have focused on some major approaches. There are diverse variant works, and we summarize the recent works. If you have any interest in this research field, please refer to the works. This is a reference for the presentation. Please refer to the paper for a more detailed explanation. This is our group who support our research. Thank you for your listening. And okay, I can check the question. The question is, thank you for your presentation. It is very informative. I wonder if there is a way to figure it out. What are the invariant features when we do not know, and maybe try to augment the data set or create a new where we can try to focus on those features. Okay. Maybe the question from my opinion, maybe the question is, what when the label is not accessible, and also we do not know which one is the causal feature, then how can you figure out which one is the important features or causal features? Maybe there, in my opinion, there is an open problem. Or if we remove if we do not consider the causality, if we only consider the correlation, then there are diverse types of algorithms to infer the importance of features, right? Such as Shapley value or influential function. However, that kind of thing does not consider the causality. Recently, I heard that and I saw that some research works, such as causal Shapley value, find the relationship between find the importance of the features on the causality range. However, the most works are limited to the tabular data set, and I think that the importance of each features in the causality range on the image or text data set is still open problem. Okay, and If you have any more questions, please type it freely.
Are there any more questions? Feel free to type them in the Q&A box. I think there are no more questions. So maybe I'd like to thank Professor Sang for this interesting presentation. Thank you very much. And thank you everyone who joined us today. We will stay, I think, for another few minutes, just in case other questions come up. And we hope to see you in our future events. We have a few events coming up. Just check our website. Thank you.
Thank you.